Every day, 647 million gallons of crude oil are refined into gasoline somewhere on this planet. The average American driver burns through 500 gallons of it every year. You've stood at a pump hundreds of times, watched the numbers climb, replaced the nozzle, and driven away. But the liquid that flows through that hose has been through one of the most extreme industrial transformation processes on Earth before it arrives in your tank. Most people have no idea what the process actually looks like. This is what actually happens. It begins not at a refinery, not at a pipeline terminal, but deep underground, in porous rock formations where organic material has been compressed and cooked by geological pressure over millions of years. What we call crude oil is the result of that process, a dense, dark mixture of hydrocarbon molecules laid down long before human beings existed. To reach it, drilling crews bore wells through hundreds of thousands of feet of rock, relying on the natural pressure trapped inside underground reservoirs to push the oil toward the surface. When that pressure falls short, mechanical pumps take over, drawing the crude upward and into the surface infrastructure that starts it on its industrial journey. Not all crude oil is the same. It comes in varying grades: light, medium, heavy, and extra heavy, each with its own viscosity, density, and sulfur content. For gasoline production, the most desirable crude is what the industry calls light sweet crude, low density, low sulfur, relatively easy to process, and generous in the proportion of high-value products it yields. Heavy sour crude exists in vast quantities around the world, but it demands additional and expensive processing steps to reach the same outcomes. What comes out of the ground determines, in large part, how much work the refinery will have to do. From the wellhead, the crude oil begins a journey that may span entire oceans. Pipelines carry it across continents, supertankers haul it across open water, rail and barge move it through inland corridors. A company like Valero, one of the largest refinery operators in the United States, takes delivery of roughly 2.2 million barrels of crude oil every single day, sourced from suppliers across the globe. When the crude arrives at a refinery, it enters storage, vast tank farms capable of holding tens of millions of barrels, where it waits until it is called into the first stage of processing. The first stage is distillation, and it is where the real transformation begins. The crude oil is piped through large furnaces and heated until the majority of it vaporizes. The resulting mixture of liquid and gas is then fed into the heart of the refinery, the atmospheric distillation tower. These are the tall, slender, rocket-shaped structures that define the skyline of every petroleum refinery on Earth, rising hundreds of feet into the air, connected by a web of pipes, ladders, and instrumentation. Inside those towers, something elegant and precise is happening. As the vaporized crude rises through the column, it begins to cool. Different hydrocarbon molecules condense back into liquid at different temperatures, and because of this, the tower acts as a kind of molecular sorting machine. The lightest fractions, with the lowest boiling points, rise to the top and are collected there. Heavier fractions condense lower down, drawn off at different levels as they reach the temperature at which they liquefy. At the very bottom of the tower, the heaviest material of all, thick, viscous residue, collects and is removed separately. Diesel, jet fuel, kerosene, heating oil, and the lighter gasoline vapors all separate from one another in this single continuous process, each claiming its own position in the column based purely on the physics of what it is. Some of what emerges from the distillation tower can move directly toward market, but a significant portion, particularly the heavy fractions collected at the bottom, has limited commercial value in its current state. Refiners do not leave that value on the table. Instead, those heavy streams are fed into what is called a conversion unit, and the most widely used conversion method is cracking. Cracking is, in precise terms, what the name suggests. Inside tall, thick-walled reactors operating at intense temperatures, heavy hydrocarbon molecules are broken apart into smaller, lighter, more valuable ones. Fluid catalytic cracking units use a fine powdered catalyst at high heat to drive this process at scale, generating large volumes of gasoline and other lighter products from material that would otherwise be low-value, heavy fuel oil. Hydrocracking units add hydrogen to the equation, producing cleaner, higher quality output and giving refiners more control over what they yield. Beyond cracking, other conversion processes work differently, not breaking molecules apart, but rearranging them. Reformers take lower octane naphtha streams and restructure their molecular architecture into higher octane gasoline components through carefully controlled chemical reactions. Alkylation units take smaller molecules and combine them into larger, more energy-dense ones. Each of these processes generates what are called intermediate streams, partially processed hydrocarbon blends that will eventually be combined into a finished product. At this stage of the refinery, dozens of these streams are moving through different units simultaneously, each one a building block in transit. Before any of them become finished gasoline, they must be cleaned. The primary concern is sulfur. Sulfur occurs naturally in crude oil in varying concentrations, and it is problematic both in the refining process itself and in the final fuel. It degrades catalytic converters, contributes to air pollution, and corrodes engine components. Desulfurization units, also called hydrotreaters, use hydrogen to strip sulfur compounds from the various product streams, bringing sulfur levels down to the tight specifications required by environmental regulations in most markets. The sulfur that is removed is not discarded. It is collected, processed further, and sold as elemental sulfur, a raw material used in fertilizer production, antibiotic manufacturing, and a range of other industrial applications. Even the impurity becomes a product. What remains after treatment is a collection of refined streams ready to be assembled into the fuel that will eventually reach consumers. This final stage is blending, and it requires both precision and expertise. Refinery technicians combine multiple different streams in carefully calculated proportions, targeting specific octane ratings, vapor pressure levels, and regional specifications that vary by season and by market. The difference between regular and premium gasoline is primarily a matter of octane, the measure of a fuel's resistance to premature ignition inside an engine. Ethanol is frequently added at this stage or later in the distribution chain, primarily to reduce exhaust emissions and extend the fuel supply, though its inclusion also affects how the gasoline must be handled and stored. From blending, the finished gasoline moves into the tank farm adjacent to the refinery, and then into the distribution network. Pipelines carry it to terminals near major population centers. Tanker trucks carry it from these terminals to more than 100,000 retail fuel locations across the country. The entire chain, from reservoir to refinery to pump, runs through multiple countries, across thousands of miles of infrastructure, and through dozens of industrial facilities, each one running continuously, around the clock, every day of the year. The scale of it all is worth holding in mind. In 2020, the combined refining capacity of every facility operating on Earth was approximately 101 million barrels per day. And across that system, something counterintuitive consistently occurs. Refineries produce a slightly greater volume of finished product than the volume of crude oil they process, because most refined products are less dense than the raw crude they came from. The refinery does not just transform the oil, it expands it. The liquid you pump into your car in under 3 minutes has been underground for millions of years. It was extracted from a rock formation, loaded onto ships, heated inside furnaces to hundreds of degrees, cracked apart at the molecular level, stripped of its impurities, blended to precise specifications, and moved through thousands of miles of infrastructure before it reached you. Nothing about what goes into your tank is simple. Every gallon of it is the endpoint of one of the largest, most complex, and most consequential industrial systems ever assembled by human beings. If you found that as remarkable as it deserves to be, subscribe to Storyline Unknown. There's a great deal more where that came from.